Oh, I'm so tired right now. I've been coding all day and I could really use an orange, but my hands are just so exhausted from hacking all day.
Did you say you needed help grabbing an orange? Well, I was just to think. ExtendAble, the robot arm that reimagines human mechanics. Let's go check it out. Grab the orange. Wait. Before we show you how it works, let's show you how we got here. It all started when Nate asked us to pull up to the SB hackathon. Obviously, we all were down, but then the next question became, what should we make? Eventually, we landed on creating a robotic arm, and the rest of the team agreed. We found STL files on an online GitHub repository that we used to 3D print the robot arm. As soon as we got to the hackathon, me and Nate began assembling the robotic arm. After 4 hours of assembling the robot, the next step was to actually make it move. So we began reading documentation and experimenting around until we finally were able to make it work.
Oh! Yes. Finally!
Our robotic arm has a two-part backend that bridges natural language commands to physical action. In stage 1, we use natural language processing with Grok API. For example, when I tell the robotic arm, pick up the orange object, the backend listens in and quickly sends this to the Grok LLM via the Grok API. The Grok LLM then returns a structured JSON response that our backend can understand and create an action plan out of. For example, here's what the Grok LLM would return when I say, pick up the orange object. And for stage 2, we use the output from stage 1 to filter the objects based on the color criteria. We do this by using a computer vision and machine learning model called YOLO, which is great for image processing because it performs a single forward pass through a convolutional neural network. So, when the robotic arm scans its field of vision, we use YOLO to detect the objects in the frame and classify the colors. We classify the colors by calculating the HSV color space for each object, which stands for hue, saturation, value. And once we have the HSV color space, we are able to compare this to a known range of HSV values for each color in order to classify each object. This is how we are able to quickly and precisely detect the objects in the frame and filter for the object based on the color criteria we provided.
One major challenge we faced was trying to engineer a procedure that allowed a complicated robot arm with 6 degrees of freedom to autonomously navigate a three-dimensional space while only having access to one camera. The robot arm was originally designed for imitation learning, but we didn't have the computational power, time, or hardware to do so, which meant we needed to resort to other strategies. Our first idea was to eliminate one dimension at a time. First, we wanted to horizontally center the robot. After this, we planned to use inverse kinematics to move the robotic arm directly above the object. Then, we thought we could simply drop down and pick the object up. However, due to the calibration of the motors, the precision of the 3D printed arm, and the awkward camera angles, this is what actually happened when we tried to do that.
As you can see, that didn't work out so well. So we had to scrap that idea and come up with something new.
We devised a clever algorithm that allowed the arm to map its three-dimensional surroundings into a lower dimensional space that it can make estimations in. First, we fixed the rotation of the robot to be horizontally aligned with the object. By doing so, we knew that the head of the robot would lie in the same two-dimensional plane as our object. Our next step is mapping this two-dimensional plane into a linear dimension that our arm can work with. To do this, we took what the robot arm would currently see and partitioned the camera screen into 10 discrete horizontal segments. For each of these partitions, we manually programmed a series of points the arm would move through, thus essentially hard-coding a library of trajectories that our arm could select from. Then, our arm could estimate which partition the center of the object most accurately resided in and select the appropriate trajectory. This algorithm allowed our arm to autonomously locate and maneuver the target object to a specific location which we marked with a blue X.
With all that being said, let's see the robot in action. Nathan, cue it.
Grab the orange.
Once my voice command is recorded, it is processed by Grok to produce a structured command which is then sent to the arm. Once it's sent to the arm, which you can see here, it triggers its scanning process. So the scanning process consists of just slowly rotating the bottom shoulder pin joint, which allows the arm to move in a horizontal direction. And it does 2 scans, one for the target object and one for the target destination. So here it's scanning for the target object, which it knows is orange because of our voice command. And it's trying to remember what positioning allows the arm to be perfectly vertically aligned with the object. So it's beginning its second scan now, where it's scanning for the blue X, which is the target destination. And it already has the recorded positioning for the orange, and now it's recording the best positioning for the blue X. And now it's using our partitioning algorithm to grab the orange, and once it grabs it, it moves back to the recorded position for the blue X, and then releases the jaw to drop it in our desired landing location.
We are stoked to announce that ExtendAble won Best Hardware Project at the Hackathon. Thank you guys for watching, and make sure to check out our GitHub repo.